Hi everyone, and welcome to our weekly seminar. Today is my pleasure to introduce my friend, colleague, Caterina Tiburzi. So I will say a few things about Caterina and then let her talk about all the interesting stuff that she has to talk about. So Caterina did her undergrad and her master's at the University of Bologna, and then her PhD at the University of Cagliari, where she graduated in 2015. And then she moved to the beautiful city of Bielefeld in Germany to continue her work on pulsar timing. And after that, she moved to Astron, to the Netherlands, with Veni Fellowship, where she stayed until last year, 2022, when she moved back to Sardinia, to INAF as a permanent faculty member. So Caterina works on ISM studies using pulsars. She's an expert on pulsar timing arrays. And today she's going to talk about PTAs and the search for low frequency gravitational waves. So Caterina, thank you very much. And the floor is yours.
Thanks a lot. I also want to point out the beautiful and existing city of Bielefeld in Germany.
Well, not convinced about that yet.
So thanks a lot for this. And so today I'm gonna give you an overview about the experiments of pulsar timing arrays that, as John was mentioning, search for low frequency gravitational waves. So this is the outline. I'm going to give you some notions about the detectors that we are using, that are pulsars, in particular millisecond pulses, and the technique that we are applying, that is pulsar timing, the generalities about pulsar timing arrays, and the main target of our search, and then a couple of mentions to so the state of the art. So where are we now, and the latest discoveries by pulsar timing arrays experiments and collaborations in the world, and yeah, my favorite or my main topic, low frequency pulsar astronomy and the effects of plasma on propagation of radio emission from pulsars and the impact on pulsar timing arrays. So I think you all know what pulsars are, but just to bring everyone on board, pulsars are highly magnetized, fast rotating neutron stars that generate two, let's say at level 0 of simplification, two beams of emission that are radiating from the magnetic poles of the stars, and they are usually powered up by the kinetic, rotational kinetic energy of the pulsar. And these beams co-rotate with the star. Typically, the rotational axis and the magnetic axis are misaligned, so these two beams of emission sweep the space. They are mainly visible at radio frequencies. So pulsars, if the geometrical conditions, sorry, excuse me, just give me a second. Sorry, I have to mute my colleagues in the room. So, as I was saying, these two beams sweep the space, and if the geometrical conditions allow, pulsars can be seen as periodic sources by an observer on Earth. If one of the two beams of emission crosses the line of sight of an observer. This is something that is very similar to what happens with the lighthouse, and in fact, the fact that pulsars are seen as periodic sources is called also lighthouse effect. As I was saying, pulsars are powered by their own kinetic energy. So that means the emission of pulsars is powered by their own kinetic rotational energy, and that means that while pulsar emit, they also slow down their rotational speed slows down. So it is possible to put together a plot like this that is called the PP dot diagram, where in the x-axis we have the logarithm of the period, the rotational period of the pulsar, and in the y-axis we have the logarithm of the spin down, so the p dot value of the pulsars, and these are all the pulsars that are currently known. And as you can see, they almost naturally divide into two big groups that we can identify as the normal pulsars that are characterized by relatively slow rotational periods above, let's say, 30 milliseconds in a rotational period, and relatively fast spin downs. So they rotate slowly and they spin down relatively fast. And another group of pulsars that have rotational periods in the order of the milliseconds, so they spin very fast, and also are characterized by very slow values of spin down rates. So they spin down very fast and they slow down very slowly. These are called the millisecond pulsars, and for their characteristics, they are also the most stable, rotationally speaking, among the known pulsars. That means it is possible to predict the arrival time of the radiation from millisecond pulsar on Earth that correspond to the rotation of the pulsars with very high precision. And this is why, because of their stability and of their predictability, if you want, that millisecond pulsars are the targets of pulsar timing arrays. Pulsars are usually studied through a technique that is called pulsar timing. In pulsar timing, we start with a relatively precise ensemble of parameters that describe the pulsar, including their astrometry, like right ascension declination, their spin period and spin period derivative, proper motion, orbital parameters, if they are in a binary system, and so on. And starting from this ensemble of parameters that we always refer as a timing model or parameter file, it is possible through a series of equations to predict, to model the arrival times of pulsar radiation on Earth. Once that you have the model, you can go to your favorite telescope to observe the pulsar for which you have the parameters, and you can derive the real arrival time. So you can observe when effectively the radiation arrives on Earth. And you can compare the observed arrival times with the modeled arrival times, and you can build residuals with that. So you can understand that if my parameters are relatively precise, then probably my residuals can be basically considered white. So they are going to be white because I'm able to predict the arrival times pretty well. However, so this would be the situation that we have here on the left. So here you have the time in x-axis and the residuals of timing residuals on the y-axis, and you can see that it's relatively white now. However, if your parameter file, if your timing model is not so precise or something is missing, then the residuals will not be white, but will be characterized by long-term structures, like you can see here on your right. So if you take the power spectrum of the timing residuals that are described here, you can see that the power spectrum is going to be something like this. No? So you have a lot of power at the low frequencies and less power at the high frequencies. So this is something that we call, as you probably all know, a red power spectrum. So everything that causes a red power spectrum in the timing residuals is referred to as a red noise. So red noise can be a lot of things, can be caused by a lot of things, can be due to some instability in the rotation, for which some intrinsic instability in the rotation, for which we are not able really to predict the rotation of the pulsar perfectly, and it is basically impossible to predict it. So this is something that we refer to as a spin noise or intrinsic red noise. It can be the interstellar medium that, as we will see later on, it causes some unpredictable delays in the arrival times of pulsar radiation at Earth. And given that the interstellar medium is organized, it creates these long-term trends. So it is also a cause for a red noise. It can be, for example, incorrect planetary ephemeris, but especially interesting for us, a red noise can be induced by gravitational waves. How do gravitational waves cause long-term trends or red noise? So why gravitational waves introduce deviations in the predicted arrival times? So just to give a general idea, I'm not an expert in this, so I'm not going to go too much into the details of this, but gravitational waves, as you know, affect the space-time, affect the space-time around us. So you can think that in particular, gravitational waves can compress and expand the space-time between us and a certain object. So when, for example, we don't have any gravitational wave between a certain pulsar and us, then a certain signal from a pulsar arrives to a certain time. But if, for example, the space-time is affected by gravitational waves, and for example, gravitational waves compress the space-time between a pulsar and us, then the same signal from the pulsar will arrive earlier than expected. And if the space-time is expanded instead, then the same signal from the pulsar will arrive later than predicted. So you can see that how this can create delays in the expected arrival times of pulsar radiation. So in theory, this gives us some leverage to make pulsars, to use pulsar as gravitational wave detectors. But now the first question is, what frequency of gravitational waves would we be able to detect with pulsars now? So we can look at the gravitational wave spectrum as we currently know it. So we know that gravitational waves in the frequency of the Earth to hundreds of Earths is a frequency window that is covered by ground-based interferometers like LIGO and Virgo. And LIGO and Virgo have detected gravitational waves coming from mergers of neutron star binaries or black hole binaries of stellar masses. If we go lower in the frequency of the gravitational wave spectrum, we have the frequency range of the microhertz that is covered by experiments like LISA, for example, a space-based interferometer for which a prototype was launched not long ago and got great results already. And at these frequencies, we are going to have mergers again of stellar mass compact binaries. So let's say that LISA would be able to detect, let's say, the previous stages of the same objects that are seen by LIGO, but also mergers of supermassive black hole binaries. So we know from the theory of galaxy evolution that there should be galaxy mergers, and given that at the center of each galaxy there is a supermassive black hole, we can picture that the merger of two galaxies can create a supermassive black hole binary. If we go lower in the frequency range of the gravitational wave spectrum, we have the nano-Earth window. And the nano-Earth window is where pulsar timing arrays work. Pulsar timing arrays in particular target supermassive black hole binaries that are coalescing in stages earlier than what LIGO would be able to see. So pulsar timing arrays should be able to see the gravitational waves coming from the coalescence of a supermassive black hole binary before the actual stage of the merger, while space-based interferometers should be able to detect the merger itself. And then at very low frequencies, we have experiments involving the cosmic microwave background. Okay, so this is the frequency window where, in theory, we are going to work with pulsar timing arrays. Now, let's assume to have a supermassive black hole binary, like isolated in the entire universe, that is coalescing. And let's assume to have one pulsar that we know perfectly, and that this pulsar is going to be, the space time between us and this pulsar is going to be affected by the gravitational waves coming from this supermassive black hole binary merging. So what would be the functional shape in the timing residuals I should expect from the gravitational wave presence? It's going to be something like this. This relatively long and complicated formula that includes some parameters of the gravitational waves like mu and psi that are the polarization angle and the polarization angle of the gravitational waves and the angle between the observer, the gravitational waves, and the pulsar. And there is this part that is now underlined by this line that carries these functional forms R. And these functional forms R show that in reality, the functional form in the timing residuals doesn't depend on the space itself between the pulsar and the Earth. So what happens in this space, but only depends on what happens at the pulsar level, as underlined by here in green, and what happens at the Earth level, as it is highlighted here in orange. And in the pulsar term appears D, and D is the distance between the Earth and the pulsar. It is important to note this parameter because the distance between the pulsar and the Earth is something that usually it is very difficult to know with very high precision in pulsar science. And so in reality, when we are looking for gravitational waves, it is extremely difficult to model this term, the pulsar term. We can safely say that in reality, in gravitational wave searches, we only use the modeling of this term, the Earth term. So how likely it is that we detect a single source of gravitational waves? So how likely it is that we detect only one individual supermassive black hole binary? It is very unlikely, really unlikely. This plot comes from a paper from the European Pulsar Timing Array collaboration, and it shows the probability of detection given the frequency of coalescing. Sorry, given the frequency of the frequency of the gravitational wave and the amplitude of the gravitational wave. And you can see that even the most likely combinations of amplitude and the frequency of the gravitational wave arrive to just 10 to the minus 6. So, and this bunch of curves are the current sensitivities that we have per frequency of the gravitational waves. So you can see that it is really unlikely that we are going to detect a single gravitational wave source. Of course, the hope is never lost, but it is very unlikely. So how do we save the day? So in reality, we don't have to focus only on one individual source of gravitational waves. We don't have to focus only on searching for one supermassive black hole binaries. What we can look at instead is the incoherent superposition of gravitational wave emissions coming from an ensemble of supermassive black hole binaries, because of course there is not going to be only one supermassive black hole binary in all the universe. There must be many. No, again for the hypothesis on galaxy evolution. So if we can picture this population, we can also think that there is a background of gravitational waves that are summing from each of these supermassive black hole binaries that are coalescing. This gravitational wave background, or GWB, is what pulsar timing arrays aim to detect first, because the amplitude, the loudness, if you want, of this gravitational wave background is going to be much more intense than the loudness of a single individual supermassive black hole binaries that is coalescing. So this is the target. And how can we leverage, given the usage of, how can we search for it? So until now, we have just discussed about one pulsar that is looking for one supermassive black hole binary. But the reality is that the gravitational wave background is going to be spatially correlated, is going to induce spatially correlated signals. What does it mean? Of course, the gravitational wave background will affect the entire space-time around the Earth, and it will be the same gravitational wave background for all the pulsars in the galaxy. So the idea is that this signal, the signal induced by the gravitational wave background, must be correlated among the timing residuals of all the pulsars in the galaxy. So this is what we're looking for. We're looking for something, a signal, that is not only belonging to one single pulsar, but to all the pulsars, and it has a certain spatial correlation among many pulsars. So what is the functional form that we are looking for? Well, we can start, first of all, to look at the power spectrum that such gravitational wave background can induce in the timing residual of a single pulsar. This is going to be something like this, that, as you can see, has a spectral index of -13/3. So it is a very red power spectrum. It is a very steep power spectrum. And this comes back to what we were saying at the beginning, that the gravitational waves will induce red power spectra in the pulsar residuals. And this is only in one pulsar. If we put together all the pulsars that we have, the best pulsars, the most stable pulsars for which we can achieve a very good description in the timing model, it is possible to build something like that. Here you can see all the pulsars that the International Pulsar Timing Array Collaboration is monitoring in the hammer plot here. And here on the right, you can see a plot of correlation among the timing residuals of pair of pulsars in our array versus their angular separation. It has been calculated that in presence of a gravitational wave background, the plot of the angular correlation among pulsar pairs in the sky should assume this functional form that is called the Hellings and Downs curve. So if you want pulsars that are very close in the sky, should have a very high correlation. This is very understandable. Then the correlation should become an anti-correlation when two pulsars are 90 degrees apart. You probably know that gravitational waves have a quadrupolar nature. And the correlation goes back to be positive when the pulsars are 180 degrees apart. So this is the signature that we're looking for. If we can get all the timing residuals from all the best pulses that we have, and we can make an array, that's where the name Pulsar Timing Array comes from. And we correlate the residuals among pulsar pairs, and we get a signature like this, then it means that we have detected the gravitational wave background. To date, no detection of gravitational wave background has been made, but we're working towards it. So there are several pulsar timing array collaborations in the world. We have the European Pulsar Timing Array in Europe, of which both me and John are part of. And the European Pulsar Timing Array, the EPTA, uses 5 different telescopes to observe the pulsars that we have selected for our array, including the Westerbork telescope in the Netherlands that is currently being dismissed. Then there is the Parkes Pulsar Timing Array in Australia that uses the Parkes Radio Telescope, and the North American collaboration Nanograph that uses GBT and the VLA and was using also the Arecibo telescope, and the Indian Pulsar Timing Array that uses GMRT and the UTI Radio Telescope. And altogether, all of these collaborations make the International Pulsar Timing Array, trying to join forces because the more the merrier. To date, the EPTA is collaborating with the Indian Pulsar Timing Array to join with the separate agreement to join data sets and expertise and to go forward. So practically, how do you search for a gravitational wave background in, let's say, in practical steps? And this is really the practical pipeline stream that we have within the EPTA to date. So first of all, of course, you have to observe your pulsars for a very long period of time from different telescopes. And there are going to be people preparing the time of arrivals for each pulsar and for its telescopes, or TOAs. The TOAs are then combined all together and to make a large and rich data set. And the timing models are refined for the first time. There is then a step of characterization of all the red noise processes that are not gravitational waves to remove them, because we don't want them to pollute the gravitational waves. And then given the characterization of the noise, there is a second optimization of the timing models. Then given the best TOAs that we have and the best timing models that we have, all the TOAs from pulsar pairs are cross-correlated to search for a gravitational wave signature. And of course, that means the helix and down signatures. So where are we now? As I said, currently there is no gravitational wave detection. However, in the past 2 years, there has been a lot of excitement in the pulsar timing array community, because we have detected what seems to be a red noise that is common among all the pulsars in the sky. And this noise doesn't seem to belong to any known noise process. However, as I was saying, this noise is common among all the pulsars, but not correlated, not spatially correlated. So it is not the gravitational wave background. However, I'm not going through the math, but just giving you the final notion. Something like this is expected before the detection of a gravitational wave background. So We cannot say that we are close to the detection, but this is relatively promising, let's say. So the detection of this common and uncorrelated red noise has spurred some very intense effort from all the PTA collaborations in the world to produce new and improved data releases of TOAs and timing models and noise models. And that's where the EPTA is mainly working now. Okay, so we expect a paper splash this year. In particular, PPTA is working to have the third data release, 20 years of data for 20 pulsars. The North American collaboration is working to have a 15-year data release for 80 pulsars. And the EPTA, with the collaboration of INPTA, is working to have a 24-year data release, the second data release of EPTA for 25 pulsars plus some additional source. There are going to be a number of papers from our collaborations, mainly the release of TOAs and timing models, then the noise models, the results of the gravitational wave background search, the search for single supermassive black hole binaries, and a series of papers on the effect of plasma on pulsar radiation. So this last point is the one in which I am mainly involved. It has been my main topic in the last 8 years, more or less. And in particular, my main expertise is on a particular effect induced by plasma called dispersion. Dispersion is an effect that is caused by a variation in the group velocity induced by free electrons on propagating radiation. If you want, you can think it in this way. You can imagine that pulsars emit a certain radiation that is broadband, so it covers different frequency, all at the same time at the pulsar level. And this radiation travels across intragalactic plasma, that means the ionized interstellar medium and the solar wind. And the effect of dispersion, as I said, is to alterate the group velocity of the radiation in a frequency-dependent fashion. That means the group velocity is altered less, the higher is the frequency of the radiation. Alternatively said, if you are then observing with a telescope, you're going to see the higher frequencies of the radiation arriving first, and the lower frequencies of the radiation arriving later. This is the effect called dispersion, and the delay, delta t, between different frequencies can be quantified by a parameter called dispersion measure, and it is inversely proportional to the frequency, to the squared of the radiation frequency. The DM, the dispersion measure, is simply the integral along the line of sight of the free electrons. So if you want, is the column density of the free electrons. Now, why is plasma why is this effect interesting for pulsar timing arrays? You probably know that pulsars are high velocity objects. They are characterized by very high proper motions, and this comes from the kick that they receive during the supernova event that creates them. So they travel in the galaxy very fast, and the line of sight of an observer should follow them if we want to continue to observe them. However, the interstellar medium is not the same in the entire galaxy. So as soon as the pulsar travels through the sky and the line of sight follows it, the line of sight crosses through different parts of the interstellar medium characterized by different column density of the electrons. So that means that the DM, the parameter of the DM, is not stable for one specific pulsar, but it varies. So for example, if we want to report it to timing residuals, as we were discussing before, we can say that if we have a certain parameter of the DM in the timing model, then maybe for a certain epoch that is fine, it gives us zero centered residuals. But then as soon as the pulsar moves, the DM varies and it is not correct anymore. So the prediction is starting to be wrong. And then maybe it still varies again and it is still wrong. So you can see how the variation of the DMs can induce temporal correlated structures in the timing residuals. And this is characterized in the power spectrum by a red power spectrum. And this is also a competitor to the gravitational waves signal, because the gravitational wave signals is going to be much, much smaller, much tinier, less loud than the signal induced by the DM variations. So to neutralize the noise induced by the DM, we have typically two approaches. We can perform a spectral modeling. Typically in PTAs, we use Bayesian-based software such as like Enterprise to model the power spectra, so that we can model and, let's say, subtract them or account for them. Or it is also possible to perform punctual DM variations. That is, the DM is computed at each point in time and subtracted. However, the majority of the pulsar timing array data are collected at frequencies that are not appropriate for none of these two approaches in reality. PTA data are typically obtained at L band, that is 1.4 gigahertz. And while the effect of DM is a problem at L band, it is not, its magnitude is not large enough to allow us to compute it, to calculate it with a very high precision. So it is a lose-lose situation. We have both of the disadvantages. We still suffer from the noise given by the DM because it is there, but it is too low for us to properly calculate it. It's like a mosquito, no? So how do we solve this? The solution that we are proposing is to pass to merge to the ePTA dataset collected with low frequency observatories. Low as lower than 1 gigahertz, well below 1 gigahertz at 150 megahertz. So in Europe, we have the possibility of using an extremely performing observatory, that is the low frequency array, LOFAR. LOFAR is an interferometer that is observing below 240 megahertz. In particular, it can be used for pulsar observations optimally between 100 and 200 megahertz. And as an interferometer, well, it is a peculiar interferometer because it is not located only in a specific region, but the modules of this interferometer are scattered around all Europe. So there are several stations, as we call the modules, mainly in Germany. The majority of the stations is in the Netherlands, where there is also the core of the interferometer. In the Netherlands, in Germany, in France, Ireland, UK, Poland, Sweden, there is going to be a station in Italy as well, and so on. So one advantage of LOFAR is that we don't necessarily have to use the entire interferometer to observe pulsars. We can actually detach the individual stations and use these individual stations as standalone telescopes. So you can see as immediately LOFAR from one big telescope can fragment into a number of small and extremely useful telescopes. So we have been working for a long time on this, in particular with LOFAR and all the individual stations that can be used as standalone telescopes. We have collected a very large data set. We have started pulsar observations since 2013, monitoring more than 100 pulsars at a weekly cadence. This is a huge data set with an extreme observing cadence. And more than 40 millisecond pulsars are also observed in this context. There is another observatory that is marvelously performing, that is NENUFAR. NENUFAR is a very low frequency counterpart of the other observing campaign that we are carrying out, because it is observing below 100 megahertz. Pulsar observations, and this is located in France. Pulsar observations started in 2019. There are more than 40 pulsars monitored. Sorry, these are not are 12 millisecond pulsars, and there is a bi-weekly to monthly cadence. So these two data sets together make a real weapon for against plasma effects, because they are observing such low frequencies that the effect of the plasma are going to be extremely magnified and very easy to calculate. This is the distinction between what happens at L-band, where PTA is usually observed. And this is the frequency in the y-axis and the pulse phase on the x-axis. And here I have simulated the same effect at L-band and at LOFAR band on the right. And you can see how the same variation in DM causes such a small tilt in the frequencies of the pulse on the right, on the left, and the magnitude of the effect that we have at 150 megahertz on the right. So you can understand from here the power of low frequency observations to measure DM variations, for example. We have already carried out a few works on DM detection and monitoring. This, for example, is a family portrait, let's say, of several pulsars that you can see indicated here in the top right of each panel, where I am reporting DM variations versus time. And you can see also how we can very well detail what happens during the solar conjunctions, as they are marked by these vertical gray lines. So during each solar conjunction, of course, the pulsar is in conjunction with the sun, so it passes the closest possible to the sun. And in addition to the effects of the interstellar plasma, we also have the effect of the solar wind. And that's where this increase in DM comes from, is the effect of the solar wind. This is just a close-up on one of the pulsars, where you can see both the effects of the interstellar medium, as you can see, for example, here in this decrease of the baseline in the DM variations, and the effects of the solar wind in these more massive surges of DM, again, during the solar conjunction. This is the same pulsar. No, sorry, this is not the same pulsar. This is another close-up, but also adding the NENUFAR data to it, that are the data in red. And this is just to show that the lower you go again in observing frequency, the higher is the precision in calculating the DM. So the red ones are the data that come from 50 megahertz in frequency, and the gray and black ones are the one coming from 150 megahertz in frequency. LOFAR currently is transiting to an upgrade. We are going to get LOFAR 2.0 stations soon. That is going to be an hardware upgrade, mainly also to allow like simultaneous observing between low parts of the antenna and high part of the antenna and so on. We are also transiting to what are called the large proposals. So let's say that the observations will be carried out within large programs instead of individual small proposals. And we have one proposal, well, one expression of interest placed for LOFR 2.0 to continue to monitor pulsars for, especially for PTA experiments. So this is ongoing, and we are currently working within the EPTA to perform a full merging and a full combination between EPTA dataset, LOFR dataset, and NINGFAT dataset. And that's all, and I thank you for your attention.
Thank you very much, Caterina. I'm doing the sound effects for everyone. Are there any questions for our speaker?
Yeah, can I ask, hi Caterina, this is Vasilis.
Hello.
You mentioned that it is unlikely that individual gravitational waves would be detected, right?
Yeah.
It's because we sort of like, we already know the possible strength of the signal from supermassive black hole binaries, for example, based on the distance they have from our galaxy.
Yeah.
Naively, I would have imagined that statistically, since in the universe we always have something really bright that comes up, that you could see something bright and then a background, right? But you seem to exclude it.
I mean, so currently, let's say with the simulations that our colleagues are performing, we are arriving to a redshift of 1.5, so it is not extremely remote. But yeah, they are calculating that most likely it is going to be extremely unlikely for a single source to stand up from the background. Not because the background covers it, of course. It's just because
the signal itself is faint to begin with.
Yeah, exactly. Like here, for example, we are considering these are, to be fair, again, these are horribly loud gravitational waves, for example, in this plot, because an individual source with an amplitude, with a gravitation, emitting a gravitational wave with an amplitude of 10 to the minus 13 is already extremely high, really, really high. But yeah, again, as you can see here, the probabilities with the current sensitivities that we have are really, really low. And this depends, unfortunately, on the precision that we can reach with the timing residuals. In the sense that, of course, if we were able, currently that our timing residuals can, if we are lucky, can reach an RMS, weighted RMS of say 100 nanoseconds. Probably if we would be able to go lower, then our sensitivity would be much higher. But given the precision, well, not poor precision, but the limitations that our
clock has.
Yeah, that our clock, exactly, very good. That our clock has, this is the best that we can do for now.
And just on the same part, scintillation would actually create an upper limit to how, you know, because of the differential application to that, to your sparse grid, would that create also a limit to how low you can go irrespective of the clock or not?
Do you mean scintillation on the pulsar or scintillation
on the pulsar?
Oh no, I mean scintillation is not a particular. I thought scintillation of the gravitational waves, because I think there are some very progressive applications on the on scintillations of gravitational waves as well. No, scintillation is not a huge problem. No, because in the end, scintillation only can only increase or decrease a bit our the error bars on the time of arrivals, but it is not what is really making the difference. The difference is made by these underlying red noises and our ability to also to take care of the white noise. I mean, if you want, scintillation contributes to the white noise, but the real problems are not there currently.
Okay, thank you very much.
Yeah, of course.
Great talk.
I think, Caterina, I may disagree a bit on what you said about the continuous gravitational waves. I guess what you want to, I would phrase it another way. I would say it's unlikely that continuous gravitational waves will be detected first.
Oh yeah, of course. Yeah, I mean.
So
yeah.
Eventually, I mean, as the sensitivity becomes better and better, then eventually we'll be able to resolve individual sources as well. But it is highly unlikely that the first signal that will be detected will be a single source.
Yeah, I mean, let's say.
Not impossible, but.
Yeah, come on. I mean, you know, if we had the SKA, then everything would be solved. But yeah, okay, I can agree with you. But
is that a fair statement? Almost fair statement.
What do you mean?
I mean that eventually, I mean, we'll detect.
I think, well, yes. Excuse me. I think, in fact, I think I was a bit too much pessimistic. You're right, in the sense that the longer we observe, for example, the longer we make our data sets, for example, the better our sensitivity will become. So it is true that eventually we are probably going to see one single source. I think it's also a matter of using another, like, new generation set of telescopes as well. Like Meerkat.
Yeah, and I think the other thing that could possibly help is high cadence observations. Like if we have a daily cadence timing.
Yeah, of course.
Which, as we hope to do with Argos.
Oh wow! Okay, maybe Argos will solve everything.
That could also help. Anyways,
oh yeah, of course, yeah.
Any other questions? I do have a question about the LOFAR DM applications that you showed. Yeah, so this is, I mean, this is a, you know, a very beautiful, very beautiful result. It's amazing how well you can see the solar wind and everything.
Yeah.
But on the other hand, that's very different from, you know, what we see at higher frequencies.
True.
So how optimistic are you that we will be able to benefit from this data set, combine it with a higher frequency data and benefit from that, given this you know, these differences? I mean,
I am fairly optimistic in the sense that you're right. There are several things that I think this is also a branch of science that is quite new with this precision, in the sense that until now we never had access to anything like this, really anything like this. So it is quite of a new sector to explore. But I am fairly optimistic, especially on the spectral modeling. That is my hope, and what me and my collaborators are pushing towards is to use LOFAR data to create a pool of statistical characterization of spectra. In particular, if we can, of course, the spectra that we can derive from LOFAR are going to be way more precise than anything that we can hope to get with higher frequency data. And if we can derive the spectral characterization of DM noise from the local data, then the parameters of the DMs, then the parameters will be the same that we should inject in the higher frequency data. And this is going to avoid any kind of complication, for example, with peculiar effects like chromaticity, for example, because the chromaticity is an effect that affects the higher frequencies of the spectrum, but is not going to affect the low frequency parts of the spectrum that are the ones that we are most interested in. And so again, this thing cannot be done for all the pulsars because not all the pulsars that are visible from EPTA and timed from EPTA are visible at low frequencies. But we are going first to test this on a small set of pulsars. And then my long-term view would be to generate a database of spectra from all the pulsars that we are looking with LOFAR that are with astrometrical correlations. That is, I hope to correlate the characteristic of a certain DM spectrum with the galactic regions. And this will allow us to also characterize pulses that are not visible in both of the bands, but we can share the parameters in this way. So I'm fairly optimistic, but of course it is, there is a lot to do. So there is a lot to test and a lot to do.
Fantastic. Okay, so I guess we're running out of time. Is there any final question for our speaker? Going 3, 2, 1. No, so okay, Caterina, thank you. Thanks a lot again.
Thank you to you.
And hopefully next time in person. I mean,
I really look forward for that.
Yeah, we too. Okay,
Thank you.
Bye everyone. See you next week.
Bye.